integration, reduced integration. So well, let's write down Pascal's triangle real quick. So we can get this with a single point. We can get this with a 2-point 2x2 quadrature rule. So we're going to define full integration as the quadrature rule of sufficient accuracy to exactly integrate all coefficients of the element stiffness matrix of the undistorted element or the parent element. Right, so our element stiffness matrix for plane elasticity would have terms of the order for Q4. Those are both squareds. So we need a 2x2 rule for that. For Q8, we need 3x3. If the element is distorted, we still call full integration the rule on the parent element. So whatever rule we define as full integration on the parent element, no matter what the real physical element looks like, that's still the full integration. Right? So then underintegration, also known as reduced integration, is when we use a rule that is less than exact. This reduces the computation time. Can offset parasitic shear. And this occurs because some of the polynomial terms will vanish at the Gauss points of lower order, and therefore they don't make any contribution to strain energy. But it does introduce a defect, namely spurious modes, singular modes, zero energy modes, hourglass modes. So they're all the same thing, they're just different names you might see in literature. So if you consider sort of all of the possible deformation modes that a Q4 can go under, a few of them are rigid body, right? So one would be rigid body translation up. Two would be rigid body translation left-right. Three would be a rigid rotation. Four would be a uniform isotropic expansion. Or compression. 5 would be an elongation. 6 would be a uniform shear. 7 would be this guy. I don't know what you call that. 8 would be this guy. And recall that sigma x y is equal to this in bending. And so, because if you use a single point integration, x would be 0, this term would go away, and you'd recover. Remember, the classic Euler-Bernoulli had 0 shear strain and bending, right? So if you evaluate that, so that would allow, no resistance to these type of deformations, which this is also what gives you the hourglass. And it always occurs in an hourglass because if you have two Q4s, there's another one attached to it, and they're tied at the nodes. They have to be continuous, right? So this is going to have the opposite deformation.